This is the screencast for section 1.2, example 5. We're going to look at continuity on functions. Already you've seen a few graphs that we've done that have these breaks. We call them discontinuities. There's three different types of discontinuities. First of all, if your graph is continuous, there are no breaks. You can basically draw the whole graph with one stroke of your pencil. You do not have to pick your pencil up. A removable discontinuity has only one tiny little point removed. So they symbolize that on a graph usually with an open circle. And sometimes that point that has been removed can be put somewhere else on the graph, but it doesn't have to. This is caused by any x value that makes both the numerator and denominator 0. So for example, if I have y equals x minus 3 in the numerator and x minus 3 in the denominator, positive 3 will make both the numerator and denominator equal to 0. A jump discontinuity is a function that continues on a path of one equation and then suddenly jumps to a totally different path or another piece of the function. This is caused usually by a piecewise function, or we have a basic function that you'll learn about in the next section, the integer function. But basically it's caused by a piecewise function that does not line up. So you have this vertical leap between, or a vertical jump between one piece of the function and another. An infinite discontinuity, named appropriately enough, when it occurs when the graph travels both up to infinity and down to infinity, or just up to infinity or just down to infinity. But basically your pencil would have to go all the way down to infinity, then pick up, and then start over again from another infinity and travel on. So an infinite discontinuity is when the graph approaches infinities from either side of that x value. That's caused by an x value that makes only the denominator 0. So let's look at example 1, or example 5. Identifying points of discontinuity. Judging from the graphs, which of the following figures shows functions that are discontinuous at x equals 2? Are any of the discontinuities removable? So I'm going to look over here, and visually I see some sort of infinite discontinuity here, but is that at 2? Is that at 3? Is it at 1? I don't know, it's hard to see. So graphically, visually, I can see an infinite discontinuity. Now I'm going to look algebraically at the function, and I can see that when x equals positive 2, the denominator will be 0. So I can say that there is an infinite discontinuity at x equals positive 2. The function, when the x values approach positive 2, will travel to the infinities. We have a break that reaches positive and negative infinity. Now in the second figure, I don't really see any discontinuities. I think this is going to travel forever. So I'm going to look at the function. Yeah, I can add 3 to anything. I can subtract 2 from anything, and then I can multiply those together. So there's really no x values that I can plug in, and no reason why there would be a break in the graph. So this would be a continuous function. This one over here, I see a removable discontinuity right there. They've symbolized it where x equals 2. They've symbolized it with a little circle. Now I'm going to look algebraically just to make sure that makes sense. So h of x equals, now the numerator can get factored, x minus 2 times x plus 2. And I still have an x minus 2 in the denominator. So in fact I can see there the positive 2 makes both the numerator and denominator 0. So there is a removable discontinuity at x equals 2. Now there's a trick. I can actually find out what y value would fill in that little hole. I can remove this problem. So if I take x minus 2, x plus 2 over x minus 2, I can remove the issue that's causing the discontinuity. And then I can find out what will happen when I plug in 2 2 plus 2 is 4. So the y value that's also missing is 4. Technically, there is a removable discontinuity at the point 2, comma 4. 2, comma 4. The now try problem, for example 5, discontinuities, is number 21. The directions say graph the function and tell whether or not it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it's removable or non-removable. Well, I don't even need to graph this function. I can look and see that 0 is going to make the denominator 0 only, not the numerator. So I can tell you there is going to be an infinite discontinuity at x equals 0. But just to make sure, I am going to graph. I'm going to say 3 divided by x, zoom 6, and I think there's a removable, or excuse me, an infinite discontinuity here at x equals 0, so I'm going to hit trace, and I can even see right there. There is the x value 0, but no y value that belongs with it, so there is some sort of break in the domain here, and I can see that my graph will travel to the infinities, so there is an infinite discontinuity at x equals 0.